Hello, in this video we're going to look at the probability of combinations of events. So when we combine events together, so event A and event B, or event A or event B and so on, what is the probability of those new events occurring? To do this, we're going to do some arithmetic with probabilities, and we would have seen a couple of these before. So let's think about the probability of A not happening. If we know the probability of A happening, it's quite simple to find the probability of A not happening. Not A is the complement of A. So the probability of the complement of A is 1 minus the probability of A. Why is that true? Well, A and the complement of A form a partition over the sample space. They are mutually exclusive, so you can't have both A and not A at the same time. And their union forms the whole sample space, because we can't have anything that's not either A or not A. So as they form a partition, we can add up all their probabilities to make 1, and so we get this formula: the probability of the complement of A is equal to 1 minus the probability of A. We've seen this identity before. This was one of our axioms of probability, and that says if A and B are mutually exclusive, so if A and B can't happen at the same time, then the probability of A or B happening, that is the probability of their union, either one or the other or both happening, is equal to the probability of A plus the probability of B. And another identity we have is that if B is a subset of A, okay, let's think, what does that mean? If B is a subset of A, then every time B happens, A must also happen. For example, if B is the event rolling a 1 on a die, and A is the event rolling an odd number on a die, then every time we roll a 1, we also roll an odd number. Okay, so B is a subset of A. And if that's the case, then the probability of A but not B is the probability of A set difference B, and that is the probability of A minus the probability of B. But these are not always the case. We don't always have these mutually exclusive or subset events. Sometimes we get more messy things. So we have to start thinking more generally. So if we have two general events, and they could happen at the same time, they could happen not at the same time, so they might not be mutually exclusive, they might not be subsets of each other. Two general events, A and B. We are now going to start building up a formula to be able to treat probabilities of these events and combinations of these probabilities. So look at our Venn diagram, because this is going to help us a lot here. What is the probability of their union? And we know their union is everything in that yellow highlighted bit of the Venn diagram there. The probability of their union, well, we can start by taking the probability of A happening. And we've got this bit of B left over. So we can add the probability of B happening. But now look, we've added a section of that yellow thing twice. That purple bit we've added twice because it's in both A and B. It's accounted for by the probability of A and the probability of B. And what is that section? That is the intersection of A and B. So we need to take that away. The probability of the intersection of A and B. We need to take that away. And this formula, probability of A union B, is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. This is a very useful formula that we'll be using a lot. Let's look at some examples. So consider this situation. There is one person in a room. What is the probability that they were born on Christmas Day? Okay, what is the probability of being born on Christmas Day? Well, we only have one event here, so we can treat this as we've been treating things before. The probability of being born on any day of the year is equally likely. And so we can think about what is the size of the event we care about divided by the size of the sample space. Well, we only care about being born on Christmas Day, so there's only one day we care about being born on, and there are 365 days in a year. So the probability of being born on Christmas Day is 1 divided by 365. So our next example we're going to look at, now there are two people in the room. What is the probability that they were both born on Christmas Day? So now we have two events and a combination of those events. Okay, what's the probability of two people being born on Christmas Day? Well, if we think about this as a sequence of events, it's not a sequence because the order doesn't matter, but if we think about this as a sequence of events, we need our first person to be born on Christmas Day, and then we need our second person to be born on Christmas Day. We can treat this as a sequence of events because the other order, the second person being born on Christmas Day and then the first, is just exactly the same. It's not a different way of getting to the same answer. They're both the same way of getting to the same answer. So what is the probability of the first being born on Christmas multiplied by the probability of the second being born on Christmas? Well, we know the probability of one person being born on Christmas Day. We just looked at that. That was 1 over 365. What's the probability of the second person being born on Christmas Day? Well, the fact that the first person was born on Christmas Day doesn't affect it, doesn't change its probability at all. And so that is also just 1 over 365. We can multiply those together. Remember, multiplying fractions, we multiply the top and multiply the bottom. So that is 1 over 365 times 365. And that actually works out to be 0.0000075. So that's something really, really, really small. And now we can ask the question, if we have two people in a room, what is the probability that at least one of them was born on Christmas Day? So this is two events, person 1 being born on Christmas Day and person 2 being born on Christmas Day, and we want the probability of the combination at least 1. So the event, at least one of two people being born on Christmas Day, is actually the union of the event the first person born and the event the second person born. Now we've just seen how to calculate the union of two events. So that is going to be probability of the first being born on Christmas plus the probability of the second being born on Christmas minus the probability that they are both born on Christmas. That's the intersection. From the previous two questions, we know each of these. So we know the probability that the first is born on Christmas is 1 over 365. The probability of the second being born on Christmas is 1 over 365. And the probability of them both being born on Christmas, that was 1 over 365 squared. So altogether, that makes 729 over 365 squared. So just some fraction manipulation there, and that gives us 0.0055. That identity that we had for the probability of the union of two events can be generalized to more events. So let's consider 3 events. Probability of A union B union C. So that's the probability of at least one of A, B or C happening. So again, we're going to build this up thinking about that Venn diagram. So the first thing we can do is add the probabilities of all the events separately up. Probability of A plus the probability of B plus the probability of C. Now, which bits have we added more than once? Well, when we add the probability of A to the probability of B, we're adding up the intersection of A and B twice. When we add the probability of A to the probability of C, we're adding the intersection of A and C twice. When we add the probability of B to the probability of C, we're adding the intersection of B and C twice. So we need to take all those intersections away. So minus the probability of the intersection of A and B, minus the probability of the intersection of A and C, minus the probability of the intersection of B and C. Now try to visualize what we've done to this Venn diagram. How have we accounted for every section? So we've accounted for the lighter red bits. Yeah, that comes under just the probability of A, B and C. We've accounted for the middle in red bits because we added those bits twice and then we took one of those away. But that dark section right in the middle, we added it 3 times when we added the probability of A, probability of B and probability of C up. We took it away 3 times when we took away all the intersections. So we're actually missing that section now, so we need to add it back in again. So we need to add that middle section, which is the intersection of all 3. So when we have 3 events, we need to add up the probability of each of those events minus the probability of each of those intersections pairwise. Then we need to add back in the intersection of all 3. And if we had more events than this, we'd use the same sort of reasoning. Let's have a look at a couple more questions which use this. So the first question, there are 3 people in the room. What is the probability that at least one was born on Christmas Day? So now we have 3 people, so 3 events, and at least one being born on Christmas Day. Okay, so what is the probability of at least one of 3 people born on Christmas Day? Well, we have 3 events, 3 possible births, so we can use that formula. That is the probability of the first born on Christmas plus the probability the second is born on Christmas plus the probability that the third born on Christmas minus the probability of the first and second being born on Christmas minus the probability of the first and third minus the probability of the second and third, adds the probability of all 3 being born on Christmas. So excuse my shorthand there, I feel like I was running out of room. So we know a lot of these already. So what's the probability of the first being born on Christmas? That is 1 over 365. The second is 1 over 365. The third being born on Christmas is 1 over 365. Minus what's the probability of the first and second being born on Christmas? So that is 1 over 365 squared. First and third is 1 over 365 squared. And the second and third is 1 over 365 squared. And the probability of all 3 of them being born on Christmas is 1 over 365 times 1 over 365 times 1 over 365, which gives us 1 over 365 cubed. Now, all together we can plug that into a calculator, but we get 3 over 365 minus 3 over 365 squared plus 1 over 365 cubed, which actually gives us 0.0082. Okay, let's look at another question. So there are 3 people in a room. What is the probability that they all have the same birthday? Okay, so the probability that 3 people share a birthday is going to be probability that they were all born on January 1st plus the probability that they were all born on January 2nd plus the probability that they were all born on January 3rd, and so on. Now we could just work all those out, but we've already worked out the probability of them all being born on Christmas Day. Was Christmas Day special? No, Christmas Day was just one of the days of the year. The same calculation is going to apply to every day of the year. So that is going to be, there are 365 days in a year, 365 times the probability that they were all born on Christmas Day, or all born on the 3rd of February, or all born on April 27th, because they're all going to be the same. But we've worked out the probability they're all born on Christmas Day, so that was 1/365 cubed. Yeah, so that gives us 1/365 squared, which we've already seen is 0.0000075. And the final question we're going to look at in this video is that there are 3 people in the room. What is the probability that at least 2 share a birthday? Now this looks like, if we try to think back to our events, it looks like we're asking for something we haven't quite worked out yet, like 2 events out of 3, we haven't quite done that yet. But the trick here is to think of it in terms of events we know the probability of and identities we already know. Okay, so the probability of at least 2 of 3 sharing a birthday, that is actually the complement of something we know about. So at least 2 of 3 sharing a birthday means all 3 don't have different birthdays. And all 3 don't have different birthdays, we can work that out. So this is actually the probability of the complement of all 3 having different birthdays. We know how to, we have an identity for working out the probability of a complement of event. It's 1 minus the probability of that event. And what is the probability of all 3 having different birthdays? Well, think of this as a sequence of events. The first person, we don't care what their birthday is. They can be born on 365 of the 365 days. The second person just needs to not have the same birthday as the first person. So the second person has a choice of 364 days out of the 365 to be born on. And the third person just needs to be born on any day that the other 2 haven't already taken. There are 363 days left. This gives us a probability of 0.008.